Okay, to show you how we can use those tables to look for properties, we're going to do one example. So in this example, we have a piston cylinder assembly you can see. And inside the cylinder, we have ammonia, NH3, ammonia. What is given is the mass of ammonia is given 0.05 kilogram. Initially, it's saturated vapor, which means the end of vaporization process. There's no liquid left, only vapor. Okay. Pressure of ammonia is 0.15 megapascal. Heating occurs slowly and the piston moves freely. Okay, so what we know is piston moves freely. Like we said before, if you see this line, piston moves freely. What does it mean? You should think in your mind that is equivalent to constant pressure. So during this process, pressure is constant. Okay, and when do we stop? We stop when the final temperature is 25 Celsius. So this is the heating process. You start from saturated vapor and then you stop when the final temperature is 25 Celsius. Okay, and then what we need to do is first sketch this process on the two diagrams, P versus nu diagram and a T versus nu diagram. Second thing is we want to find initial volume V1 and a final volume V2. And the last thing is to look for work. Okay, what is my system? My system is within the dashed line and it's ammonia. Ammonia is my system. Okay, so let's start from the first one. Sketch the two diagrams. Okay, so what we do is always the same. We sketch the two diagrams. P pressure versus nu specific volume, and then T temperature versus nu specific volume. And the first thing we do is always the same, is to sketch the vapor dome. Okay, steep, less steep, steep, less steep. Okay, the two vapor domes. Okay, so now let's start from the P versus nu diagram. Okay, so we know it's a constant pressure process. If we start from P versus nu diagram, just like before, pressure doesn't change, meaning my y coordinate doesn't change. If my y coordinate doesn't change, it must be a horizontal line. All right, so everything must happen along this horizontal line because pressure, the y coordinate doesn't change. Okay, next, let's locate point 1. Where is point 1? Point 1 is the initial state. Initially, it's saturated vapor, G point. Where is saturated vapor on the diagram? Saturated vapor is the right half of the vapor dome. Okay, and it also has to be along this dashed line, so the only choice is here. That's my point 1, and it's also point G. Okay, so it requires the two requirements. It satisfies the two requirements. The first one along the dashed line. Second one is on the right half of the vapor dome, meaning it's saturated vapor. Okay, that's number one. Next one, 1 to 2. 1 to 2. What happens between 1 and 2? Heating. Heating occurs slowly. So if you heat up saturated vapor, what's going to happen? How does the volume, specific volume, nu, how does it change? How does it change? What is the definition of nu? Volume over mass, right? Okay, does the mass of the ammonia change? Mass doesn't change. What about volume? If you keep heating some gas, what's going to happen to the gas? The volume will go up. If volume go up, does specific volume go up? Yes. So meaning the x-coordinate becomes bigger. If the x-coordinate becomes bigger, 1 to 2 must go to the right. So number 2 must be to the right and also on this dash line. Okay, So 1 to 2. Number 2 is superheated. Must be superheated because number 2 is to the right of the vapor dome. It must be superheated. Okay, so that's P versus nu diagram. Remember, because volume goes up, so specific volume goes up. If specific volume goes up, the x-coordinate becomes bigger. If the x-coordinate becomes bigger, you must go to the right. Okay, so that's P versus nu diagram. Next one, let's sketch T versus nu diagram. Okay, this is a constant pressure process. So on this T versus nu diagram, just like before, we need a constant pressure line. This is a constant pressure line, meaning every point on this line has the same pressure. So 1 to 2, this whole process must happen along this constant pressure line. The first thing is we need to locate point 1. So do that again. What is the phase of number 1? Saturated vapor. Where is saturated vapor on the T versus nu diagram? Same thing, on the right half of the vapor dome. So you have to satisfy two requirements. First one, on the right half of the vapor dome. Second one, along the constant pressure line. So the only choice is here. That's where number 1 is. Also G point, saturated vapor. And next one, 1 to 2. 1 to 2. Do I go to the right or to the left along this constant pressure line? Because pressure has to be constant. And then we do the same analysis. Specific volume is equal to volume over mass. Mass doesn't change, but the volume will go up because it's a heating process. You heat up the vapor will expand, so volume becomes bigger. So specific volume will bigger. In other words, your x-coordinate becomes bigger. If your x-coordinate becomes bigger, you must move to the right. So 1 to 2, you move to the right, and number 2 must also be on this constant pressure line. So 1 to 2 to the right, and number 2 must also be on this constant pressure line because this is a constant pressure process. So number 2 must be superheated vapor because it's to the right of the vapor dome. Okay, so that's the two diagrams, P versus nu and T versus nu. Okay, so that's part 1. Now let's do part 2. What is part 2? Part 2 is to look for initial volume V1 and a final volume V2. Okay. Have you noticed in this class we usually do not directly deal with volume? What do we deal with? We deal with specific volume. Specific volume. So is it possible for us to find specific volume and then from there we can find volume? Volume is equal to mass multiplied by nu. So for V1, what do we have? If you want to find V1, you must find mass times nu1. There's no need for us to give mass a subscript because mass of the ammonia doesn't change, it's a constant. And for final volume V2, we just need to find mass times nu2. We already have the mass of the ammonia is given. So as long as I can find nu1 and nu2, then I can solve this problem. Okay? Nu1 and nu2. Okay, and then we do a small change. We change the subscript nu1 from 1 to G because point 1 is point G, right? If you take a look at the diagrams, point 1 is saturated vapor, which is just point G. Okay, is it possible to find nu G? Yes, it is. That's how we use the tables. Okay, so how do we go to tables? The table we're going to use is this one, table A14. Table A14. Okay, so first of all, make sure it's ammonia because you have tables for different substances. We have tables for just water, we have tables just for ammonia. So make sure you choose the one for ammonia. Okay, next one, the first column you can see is pressure. Second column is temperature. What kind of temperature is it? It is saturation temperature. Do you remember the definition of saturation temperature? The definition of saturation temperature is the temperature at which your substance is at a saturated state. In other words, F or G point, the temperature of F point or G point. Okay, all right, and then if you continue to the right, you will see the third column is nu F. What is nu F? Specific volume for saturated liquid. Okay, and then if you continue to the right, the fourth column is nu G. What is nu G? Specific volume for saturated vapor. And here I want to point out one thing that is really, really important that is in column number 3. Nu F, if you take a look at nu F, it's different from other columns. What is that? Nu F times 10 to the third. What does that mean? That means every number in this column has been magnified by 1000 times from its true value. So for example, the first number in column number 3 is 1.4236. This is not the true value. This is the value that has been magnified by 1000 times from the true value. So what is the true value? The true value should be 1.4236 divided by 1000. You have to go back by dividing by 1000. Okay? All right, so back to this example. The one we're looking for is, if we go back, we're looking for nu G. Nu G. Okay, how do we look for nu G from this table? How do we look for nu G from this table? Can we start from the pressure? Can we start from the pressure? So for example, if I start from the pressure, I can look for the corresponding nu G. Do we know the pressure of this process? The pressure of this process is given. It's a constant pressure process, and it is 0.15 megapascal. Okay, 0.15 megapascal. And now we go back to the table. We go to column 1. We look for this pressure. And what do you notice? Column number 1 uses bar, so we have to convert megapascal to bar first. Okay, so that's the first thing we're gonna do. We go to table A14, and then we know we have to start from pressure. The pressure we have is 0.15 megapascal. However, the table uses bar, so we have to convert megapascal to bar. Okay, the way to convert is 1 megapascal is equal to 10 bar. 1 megapascal is equal to 10 bar, so our solution is 1.5 bar. So 1.5 bar is our pressure. So now we can go back to our table, and this time we start from pressure. We know the pressure in the first column is 1.5 bar. So we start from this row. We look at this row. This is the row we look at, 1.5 bar. And what is the property that I'm looking for? I'm looking for nu G. Where's nu G? Nu G is column number 4, nu G. So you go down, you look for nu G, this column. Okay, so now what is the nu G at the corresponding pressure? 1.5 bar right here. This is the corresponding nu G at 1.5 bar, 0.7787. And then don't forget the unit. The unit is right here, cubic meter per kilogram. So this is how you find nu G at the corresponding pressure 1.5 bar. Okay, so by doing this, you realize how you can use the tables to look for the corresponding properties. Okay, so now we go back to our question, and then we write down what we found. We found nu G, and nu G is 0.7787. 0.87. And never forget the units, cubic meter per kilogram. So now you can plug in this new G back into here and find corresponding V1. Okay, so now we can find V1, which is M times new G. Mass of the ammonia is given, 0.05 kilogram times new G. New G is 0.7787. Okay, cubic meter, kilogram, everything is in SI unit. Solution 0.0389. Your solution must also have an SI unit. The SI unit for volume is cubic meter. Okay, so we're done with V1. Next one, we just need to look for V2. And V2, what's the key to look for V2? Is to look for new 2. As long as you can find new 2, you can find V2 easily. Is it possible for us to use a table, just similar to what we did before, to find new 2? The answer is yes. Let's go back to the diagram. What's the phase of number 2 again? It's superheated ammonia vapor. And we do have a table for superheated ammonia vapor. Okay, so now let's go back to the table. And now this time we move on to table A15. And then you can see this is superheated ammonia vapor table. Okay, so how do we use table A15? You can see this table is divided into different blocks corresponding to different pressures. So each block is for one specific pressure. Remember the pressure we have is 1.5 bar. So we go down this table, we find a corresponding block here where pressure is 1.5 bar. So we look at this block. Okay, and now which column is new? We're looking for new. And then you realize the second column here is new. Okay, second column here is new. Is it possible for us to start from pressure or temperature to find a corresponding new? Yes. The first column is temperature. The first column is temperature. So for example, if we know the temperature is here, if we know the temperature is -50, -50, something like this, -50, and then you can find a corresponding new easily, which is 2.6841. Right? Okay, so do we actually know the temperature corresponding to new 2? Remember, subscript 2 means final. So do we know the final temperature? Let's go back. Do we know the final temperature? The final temperature is given. Where is that? Final temperature is 25 Celsius. So now let's go back to the table. We know we're looking at this block. And then we know the first column is temperature. My final temperature is 25 Celsius. So 25 Celsius is here. So I should be looking at this row, starting from 25 Celsius. What is the corresponding new? Which column is new again? The second column is new. So the second column new. So my solution for new will just be this number. At 25 Celsius and 1.5 bar, the corresponding new specific volume is 0.9553. And never forget the unit. If you don't remember the unit, you can always go to the top of the table and it shows you the unit. Cubic meter per kilogram. Okay, so now we can go back to our problem and write it down. This time we go to table A15. It's for superheated ammonia vapor. And then we start from pressure, which is 0.15 megapascal. Because pressure is constant, pressure doesn't change. 1.5 bar. And in addition, we also used temperature, final temperature T2. Final temperature T2 is 25 Celsius. And those things together give us the corresponding nu. Let's give it a subscript, nu2, meaning its final state. Nu2 is from the table 0.9553, and never forget the unit. Okay, never forget the unit. So this is how you find nu2. And after you find nu2, you can plug it in back into this equation and then find corresponding V2. Mass of ammonia still a constant, 0.05 kilogram multiplied by nu2, 0.9553. Everything is in SI unit. The solution is 0.0478 SI unit cubic meter for volume. So this is part 2, how to look for initial volume V1 and final volume V2 by using the tables to look for properties. Okay, so that's part 2. And then the last part is W, looking for work. Looking for work. Okay, like I said, I always suggest you start from the most fundamental equation to look for work. What is the most fundamental equation to look for work? Work is equal to integral P dV. P is pressure, V is volume. Lower limit V1, upper limit V2. That is the equation. Okay, pressure. What happens to the pressure? To my integrand. My integrand is pressure of the system. My system is the ammonia. So what do we know about the pressure of the ammonia? It's constant. Pressure of the ammonia is constant, and the value is right here, 0.15 megapascal. So I have an integrand which is constant, meaning I can take it out. If you take it out, what is left is V2 minus V1. And do we have V1? Yes. Do we have V2? Yes. Do we have pressure? Yes. We have everything in the right hand side. Okay, so now let's plug in pressure. Pressure is 0.15 megapascal. Make sure you understand you have to plug in SI unit for every parameter. So we have to convert megapascal to pascal by multiplying 10 to the 6. Mega is 10 to the 6. Kilo is 10 to the third. Okay, multiply by V2, 0.0478 from before, minus V1, 0.0389. Both are in SI units. Okay, so solution is 1.335 times 10 to the third. And your solution must also have an SI unit. What is the SI unit for work? It's joules. And usually we use kilojoules. So our final solution is 1.335 kilojoules. That is how much work. Okay, so what do you notice? You notice your work is positive. What does it mean? If your work is positive, that means your system generates work. If your solution for work is negative, that means your system consumes work. Does it make sense for my solution to be positive? Let's go back to the diagram. What happens here? You have ammonia as vapor and then you heat it up, which means the ammonia will expand. So the ammonia will push the piston upwards. The ammonia pushes. So ammonia is the one that generates work, and piston is the one that receives or consumes work. So ammonia in this process actually generates work. So the work must be positive. So now let's go back to our solution. Then you can see our solution makes sense because our solution is positive, indicating generating work. Okay, all right, so this is the example. And in this example, you can see if you deal with G point or F point, you can easily go to the table, right? Let's go to the table again. If you deal with G point or F point, you can see column number 3, column number 4, nu F, nu G. You can easily find specific volume for saturated liquid F point and saturated vapor G point from the table very easily. However, what if you have a mixture? What if you have a mixture? How do you find nu for a mixture? So next one, let's talk about mixtures. Okay, Let's recall if you have the two diagrams, P versus nu and T versus nu. Vapor dome, vapor dome, and then here you have a constant temperature line. Curves down, straight, curves down. This is a constant temperature line. And here you have a constant pressure line. Curves up, straight, and curves up. Okay, so here, this is easy. F point, saturated liquid, and here, G point, saturated vapor. Here, F point, saturated liquid, here, G point, saturated vapor. Anything about F point or G point is easy to find from the table, like we did before. However, what if you have a mixture somewhere in between, right? Somewhere in between. Between F and G, that means you have a mixture of F point and G point. If that happens, how do you look for nu? Okay, so in order for us to do that, you have to start from the definition of quality. Let's recall quality. We use letter X for quality. The definition is mass of the vapor divided by total mass. And what is total mass? Total mass is mass of the vapor plus mass of the liquid. This is the definition of quality. It's a percentage of vapor out of the whole mixture in terms of mass. Okay, so X is always between 0 and 1 because it is a percentage. If X is equal to 1, what does it mean? If X is equal to 0, if X is equal to 0, that means mass of the vapor must be 0. It must mean the numerator must be 0. If the numerator is equal to 0, what does that mean? There's no vapor. There's no vapor. So F only. There's no vapor. There's only saturated liquid. Point F only. If X is equal to 1, what does that mean? If X is equal to 1, that means mass of the vapor, the numerator, must be equal to total mass, the denominator. If they're equal, that means what? Everything in the mixture is vapor. There's no liquid. Everything is vapor. There's no liquid. Everything is saturated vapor, G point. There's no liquid. And then if X is between 0 and 1, not including 0 or 1, that means it must be a mixture of F and G. You have a little bit of F and a little bit of G. Okay, it must be a mixture. So now, if you have a mixture, how do you look for the corresponding nu, specific volume? It's not F point, it's not G point, it's a mixture. How do you look for the corresponding nu for a mixture? Let's start from the definition of nu. The definition of nu, specific volume, is volume over mass. So now we know it's a mixture. It's a mixture. So the volume must come from vapor. And it must also come from the liquid. Okay, each one contributes a little bit and divided by total mass. Total mass. Ma Total mass. All right, and then let's recall. Nu is equal to V over M, so we can rewrite this equation to volume is equal to mass multiplied by nu. So now what we're gonna do is to rewrite the two volumes. So let's first rewrite volume of the vapor in the numerator. How do we rewrite volume? We can use this equation. Volume is equal to mass times nu, and this time is for vapor. And then we do the same thing to rewrite the second term in the numerator, which is volume of the liquid. And volume can be rewritten to mass multiplied by nu. And this time it's for liquid. Okay, so this is how we rewrite the two terms in the numerator. And then separate those two. First one becomes mass of the vapor divided by total mass multiplied by new vapor. Second term becomes mass of the liquid divided by total mass multiplied by new of the liquid. Okay, so now let's continue. What is mass of vapor divided by mass of total? Mass of vapor divided by total mass, right? If you forgot, you can go back. What is this? Vapor mass divided by total mass, that is the definition of quality. So this term just becomes quality. And what about this term? Can we do something about this term? Mass of the liquid divided by total mass. It's very straightforward. Okay, mass of the liquid, we can rewrite mass of the liquid into, first of all, the denominator will still be the same. What about the numerator? We can rewrite it to total mass minus vapor mass. And what is left must be the mass of the liquid, right? Okay, and then multiply by new liquid. Let's continue. X times new vapor plus, okay, mass total divided by mass total, that's 1. Next one, mass vapor divided by total mass times new liquid. And again, what is vapor mass divided by total mass? That is the definition of quality. So this equation becomes x times new vapor plus 1 minus x times new liquid. And don't forget, our left-hand side is new. Alright, so this is our final solution. If you have a mixture and you want to find a corresponding new specific volume of the mixture, you have to use this equation. X times new for vapor is G point, saturated vapor, that's G point, plus 1 minus X multiplied by new liquid. Liquid is point, saturated liquid is point F. This is the equation you can use to calculate the specific volume for a mixture. Okay, how do you memorize it? How do you memorize this equation? It's really easy to memorize it if you understand it. So let's do it again. I'm looking for nu of a mixture. Okay, so this is a mixture of how many components? Two components. What are the two components? Vapor and liquid. So first one, nu of the vapor. Second one, nu of the liquid. Okay, two components. Next one, how much does each one contribute? Nu G contributes how much? It contributes X%, which is the definition of how much vapor it has. And then how much liquid do you have? The rest, 1 minus X. Okay, that's it. If you can understand, then you can memorize this equation easily. And as we practice more, you will be more and more comfortable with this equation. Okay, to help you understand this equation and use this equation, we're gonna do one more example.